Differentiation fractures a system to measure its exact rate of change at a single frozen moment. If we want to reverse that process, if we know the rate of change and need to rebuild the entire system, we need a reverse mechanism. We use integration. It is the mathematical process of continuous accumulation, allowing us to stitch isolated moments of change back together into a complete picture. This notation represents that process. The integral symbol directs us to some infinitely small slices of the function. Geometrically, this calculates the precise area trapped underneath a curve, determining the total geometric accumulation. Analytically, integration solves broad accumulation problems over time, such as calculating the total distance a vehicle travels based on its varying velocity. This ability to track continuous accumulation is exactly how discrete computer systems model fluid real-world environments. Physics simulations and data accumulation in machine learning require tracking these continuous changes to update their internal models accurately. Mastering integration is required to translate localized, instantaneous changes into a universal, updated system state. Integrals are applied in two distinct ways, starting with the generalized state of a system. This is an indefinite integral. As the formula shows, the output is not a static number, but a new function, capital F of x, plus a constant, c. This c is the constant of integration. C represents initial state information that was wiped out during differentiation. Since any constant has a derivative of 0, we add c to account for that unknown starting value. For example, the integral of 2x is x squared plus c. Its derivative is 2x, but so is x squared plus 5. This unknown constant means the result represents an infinite family of functions, identical curves at different vertical positions. The indefinite integral provides a generalized blueprint for a system's behavior, but it doesn't provide the specific boundaries needed for a hard measurement. The second application of integration lets us extract a precise, usable number from a continuous system. This is the definite integral. By adding boundaries a and b, we evaluate the upper limit and subtract the lower limit. Evaluating across defined boundaries collapses the function into a numerical value. Integrating x from 0 to 2 results in exactly 2. On a graph, this corresponds to the area of a triangle with a base and height of 2. This specific bounded area matches the numerical answer provided by our definite integral. In computing, these boundaries map to specific intervals, like measuring signal data over a 2-second window. Defining boundaries transforms abstract mathematical blueprints into the measurable data points required for digital signal processing. Computing systems rarely process isolated polynomials. They operate on composite functions, nesting one operation inside another. To solve these, we use the substitution method. Consider this integral: 2x times the quantity x squared plus 1 cubed. We simplify by assigning a temporary variable u to the inner function. Since the derivative of x squared plus 1 is 2x, the outer multiplier is absorbed into du. This collapses the complex equation into a basic polynomial integral. Substitution allows us to mathematically simplify composite systems into calculable components. A different challenge arises when we must integrate two unrelated functions that are multiplied together. For these cases, we use integration by parts to reverse the calculus product rule. The formula reconfigures the integral of a product into a subtraction of simpler terms. Take the integral of x times e to the power of x. We assign u to the x and dv to the exponential part. This reassignment shifts the integration from a complex product to a single solvable term. These structural manipulations are the tools used to solve the complex differential equations required for realistic physics simulations. We can also apply these principles to spatial geometry. A single definite integral measures the area between a curve and the zero baseline of the x-axis. However, spatial modeling often requires finding the area clamped between two different curves. We find this area by integrating the difference between the upper function and lower function. To find the area between the line y equals x and the parabola y equals x squared, we identify their intersections at 0 and 1. We calculate the area under the top line and subtract the area under the bottom curve. This leaves only the isolated, mathematically bounded shape trapped between the curves. This mathematical logic, calculating the exact boundaries between continuous curves, is the fundamental engine used in modern graphics rendering and simulation systems. Integration serves two roles: reconstructing generalized functions from rates of change and calculating specific bounded accumulations. Through substitution and integration by parts, we can dismantle and solve complex continuous interactions. While computers process discrete bits, the physical world operates in continuity. These formulas allow us to translate those continuous real-world behaviors into digital models, from visualizing datasets to programming physics engines. Whether rendering graphics or building simulations, integration is the tool that translates localized change into a precise total value.